Bismillahirrahmanirrahim. Assalamu alaikum. So we will be talking about the difference between the stochastic integrals and the normal calculus, or the classical calculus, or the calculus that we do. So the question is, why Brownian motion changes the rules of integration. So like in normal calculus, you have already learned the integration and differentiation. So when you kind of jump into the stochastic versions, then the things get changed, and let's see why those get changed. So we will understand the Brownian motion, which is actually the random catalyst. So it is a kind of thing that changes the game. So let's define this, the building blocks or the Brownian motion. So what's a Brownian motion? So it has been named after the Robert Brown. It describes the random motion or the random movement of particles when you're talking in the fluid. So in fluid mechanics, it's the random movement of particles. So but in mathematics, it is the Wiener process. So in mathematics, we call this W sub t as a Wiener process or Brownian motion. So what are some of the axioms or some of the properties that it has to satisfy? So the properties are it has to start at 0. So at 0 it is 0. So like when time is 0, so your function, which is your Brownian, is 0. It has got continuous paths, but the paths are jigged everywhere. So you can look into the picture attached. So you can see that the blue, green, blue, and red paths or the graphs are continuous, but they are jigged. So there is jiggling. So like one of the other interesting property that W sub t has got, it is it has got independent Gaussian increments. So the increments are the increments, so like W2 minus W1 are dW. So at every time instant, so the increments follow Gaussian distribution and they are independent. One of the problematic thing that we face with this Brownian motion is they are nowhere differentiable, right? So this is something which differs from so it's a kind of function which are nowhere differentiable. So that is a problematic thing when comparing it with the usual functions, continuous functions. Thinking of a function which is nowhere differentiable, so it has kinks, are kind of so strange behavior. Okay, so the traditional calculus fails here. In Riemann-Stieltjes integration, we assume paths have finite variation. So the paths vary, but the variation is finite. But when we talk about the Brownian motion, the variation is infinite. Okay, and secondly, because the paths in the Brownian motion are jigged randomly, graphed, so you can't calculate a standard derivative. The slope at a point is infinite. So like at a point you can't calculate the derivative. Why? Because of the jigging behavior and no differentiability. So of course we need a new set of rules that can handle the microscopic volatility of random paths. So we need to define something else for computing the things. There is another interesting difference between them, which is the scaling paradox. So when we talk about the deterministic calculus or the usual calculus or the normal calculus, the increment dx scales with dt. So if x is depending on times and dx will be scaled, the dx scales with dt. If you shrink time, by half, the distance shrinks by half. So like distance is depending on time, and you're shrinking the time by 1/2, then your distance will shrink by 1/2, you know. But in Brownian, so Brownian W is also kind of depending on time, but it scales with square root of dt, right? So like random shocks are much larger than time increment at microscopic level, right? The next thing is the quadratic variation, but when we talk about the deterministic version, then for smooth function, when we talk about the increments, so t squares are ignored. Why? Because we say that these are small, so we neglect them. But when we talk about the stochastic versions, so for Brownian, the square of increment captures the variance of time. So in other words, you can say that for the deterministic dt square is 0, but dw square in the Brownian case is equal to dt. It's not 0, right? So it is not ignored, but it is, kind of taken at dt. So that's also, a difference. So the next thing that was kind of revolutionary was the Ito calculus. So Ito calculus is what it's integrating your function, which is depending on Brownian or time, with respect to Brownian. Also not only integration but also differentiation. So it starts in big in 1940s. So there was Japanese mathematician Kyoshi Ito developed a way to integrate with respect to these jagged paths. His key insight was the Ito integral. He used a left endpoint rule to ensure causality. The strategy used at time t cannot depend on the random shock at t plus dt. So when we compare the Newton versus Ito, so in chain rule, when we're talking about the differentials and normal calculus are deterministic, then differential of f is derivative of f times dx and the differential of x. But when we talk about Ito calculus, so the differential is not same as the deterministic one, but it is different. So it's the differential of f, which is depending on x, and x is depending on Brownian and time. So it is given by this quantity df to bf prime of x dx plus half second derivative of f times dx. So this dx with brackets is also calculated. So this kind of expression you find in the Ito calculus. So when we integrate x, so we get x squared by 2, but when we integrate w, which is a Brownian with respect to Brownian, or the Wiener process with respect to Wiener process, we get Wiener process squared minus t divided by 2. Causality, so future seeing allowed. So in deterministic you are allowed to see the future, but in Ito it is strictly adapted. So basic units, so in dt is a linear change and dw is a random shock. So linear change is dt t2 minus 1, while the dw, which is the change in the Brownian, is a random shock. Ito lemma, the co-formula, this is the stochastic version of Taylor expansion, because when we are in the deterministic, then dt square is ignored, but in the calculus, Ito calculus, dw square is dt. So when I'm saying Ito calculus is somehow inside the stochastic. So the second order derivative does not vanish, and the differential of f, which is depending on time, as well as Ito, as well as Wiener, is given by the partial derivative of f with respect to t dt plus partial derivative of f with respect to Brownian. It is actually x. This is later on replaced with Brownian times the Brownian differential of Brownian plus 1/2 second derivative of f with respect to the Brownian dt. So the convexity adjustment is the bridge between randomness and time. Why does this matter? So when we are talking about the quantum finance, Black-Scholes option pricing is entirely sitting on the Ito's lemma to link stock price to time decay, and physics modeling heat diffusion, molecular dynamics, and in particular particle physics, filtering and engineering. When we talk about AI and machine learning, then stochastic gradient descent and diffusion model, generative AI use these principles for noise management. So it's actually from chaos to calculation. So by acknowledging the chain non-differentiable nature of the world, Stochastic gives us the tools to price risk and predict the unpredictable. If you got any questions, you can ask in the comment section. Thank you.